So, last day on acids, bases. And there's a reason why. Okay. Because we said there's a lot more strong acids or weak acids in the world. Weak acid. You know, it's not even comparison, right? Okay. Let's ask you a couple questions here. Megan, beaker of water. I am going to put a drop of HCl in there. Will that water then become acidic, basic, or stay neutral?
Because the acid's just going to break apart.
Yeah, the acid will break apart. So it'll make this solution. You just said it. The acid's going to break apart.
Well, yeah,
So it has to make the solution acidic, right? The acid's going to break apart, so it's going to make the solution acidic, right? Break apart meaning a lot of H pluses. You have a lot of H pluses in here, so yeah, it's going to become acidic. Everyone with me so far? Okay. Steph, I'm going to drop ammonia, NH3, put a drop of that in the water. Now the solutions are going to become acidic, basic, or neutral. NH3. Now it's kind of a trick question because NH3, right, we don't see H's on it. We don't see OH's on it, but it's on that. It's in that stupid table. Remember that we had last class period. It's in the table of those bases. NH3 is. So that means the solution is going to become basic. And you have to, if you want to actually predict the pH, you'd have to do the whole ice table thing, right? Okay. Kenneth, now I'm going to put a tablet of aspirin in there. Aspirin in there. Acidic, basic, or neutral? What would happen to it?
Wouldn't it become neutral because that's not all acid because it's made of different compounds along with the acid?
Now, I hear what you're saying. But remember, even if neutral is just a nice, perfect balance. If you just add a little tiny bit of acid, even though it's really close to neutral, we still call it acidic.
Okay.
So it'd become acidic, right? So it's not gonna, 6.98 is essentially, technically we'll call it acidic, right? Okay, so that's what I'm trying to say. It's gonna make the solution a little bit acidic. Aspirin would. Okay. Now we're getting into, so that's everything we've talked about so far, those types of compounds. Now I'm going to ask you some other compounds. Jose, Tums. I'm going to put one of these in here, Tums. And I'll give you a hint. I don't know if it's going to be much of a hint. Tums is calcium carbonate. Would this solution then become acidic, basic, or would it stay neutral? Okay. He says neutral. Does everybody agree? So what you have to do is you have to first, I guess, look at the little solubility rules and see if this thing will dissolve. But even if it doesn't dissolve, it'll dissolve a little tiny bit. So even if it dissolves a little tiny bit, what are the ions here? Ca with a +2 and this with a -2. What was this guy called? Who remembers this? Andrea, what was this thing called? Carbonate. I think you said carbonate, right? Carbonate. Okay. So we have calcium ions go into solution. We have carbonate anions going into solution. So that's what we'll have. So what we're supposed to look at is we're supposed to look at both of these and see if they're going to have any acidic or basic properties. Calcium ion, no, nothing. But carbonate, what's the technical word for carbonate? Carbonate is a conjugate base. Of what acid? HCO3 minus. You could almost even argue that it's a conjugate base, like you could go even further, H2CO3. So this guy's a pretty good base. I mean, he can turn into these, he can grab 2 hydrogens actually, right? So he's a base. Carbonate is a base. So this solution, when I add a Tums in there, should turn basic, because what is a base? Carbonate is a base. Okay, so that's the game we're going to be playing. If it were only that easy, though. Okay, I picked on Kenneth. Bowdy. Table salt. What is table salt? NaCl. Okay. Table salt is NaCl. I should be writing on here instead of the chalkboard. Table salt is NaCl. Okay. I dumped this in water. Just some crystals in there. Acidic, basic, or neutral? Okay. Play the same game. Play the same game. What ions would you have? You'd have Na plus and Cl minus. Okay. Then you're supposed to look at them and see if you recognize anything. Now those metals, they never do anything. But Cl minus is the conjugate base of HCl. So right now, you should be guessing what? You should be guessing basic, because Cl minus is a conjugate base. Problem is, there's 6 conjugate bases that do nothing because they are so super, super weak. Is Cl minus one of those conjugate bases?
Yes.
Yes. Right? Because its conjugate acid is super strong. This guy, Cl minus, has to be super weak, otherwise HCl would not be super strong. So you got to be careful. There's 6 of these bases where you're just going to say the answer is neutral. So it's kind of like a trick question. The answer is neutral. They'll stay at pH 7. Okay. So that's the game we're playing today. Is we're pretty much going to have to, and we don't have a table of those bases, but we do. Okay, so let's start at the beginning again. Right now, how do we recognize a conjugate base? It has to be in the table, right? So like one of the first questions I asked Steph was ammonia, right? The only way to answer that's going to be a basic solution is, oh, it's in the base table. So no big deal, just like the quiz. Okay, what we're talking about today is our last source of these weak acid, weak base systems. We have a second source of weak bases, the table of weak acids. Okay, let's see if you can follow what I'm saying here. Andrea, I'm saying that, I don't know, if there's 30 compounds here, we should be able to name 30 conjugate bases. So let's just pick one. I'm going to circle one of these. The compound I circled, Andrea, is a conjugate acid or a conjugate base?
Acid.
It's an acid, right? It's an acid table, so it better be a conjugate acid. So what would be the conjugate base?
Would it be
OCN with a minus. Exactly. So if you wrote all the formulas for all the bases, you'd write OCN minus. Right? You can do that for everything on here. HF, you'd have F minus, right? H2S, you'd have HS minus. You can just keep on going on and on and on, right? So for every conjugate acid, it has a conjugate base. Okay. So Kendall, when we have a base in solution, we have to do ice, right? And remember, it looks kind of like, I don't know, if we had like F minus, you'd have F minus plus, how does that KB reaction go? F minus plus H2O goes to H, F, and OH. right? And then remember doing this, you guys? And then we did ice on this, and then that's how we got the P. Well, we had to get the POH, then you get the pH. Remember doing this? But we had to have a KB to do this. We don't have a KB. We just have a KA. And they're not going to give you another table. They're going to say, this is it. So you have to know how to get KBs out of KAs. How do you do it? The trick was in the reading. Ka, sorry. You look up the Ka for HF. Well, so this is in the table. Kb is what you want. But if you multiply those two together, you always get Kw. What was Kw? 1 times 10 to the negative 14. So they expect you to calculate every single Kb. So if you have a conjugate base in one of these, if you have one of these conjugate bases in water, you write your Kb reaction, you do the whole ice thing, but you got to set it equal to Kb. And how do you get the Kb? You got to calculate it. So you look up the Ka for its conjugate acid, and then you calculate Kb. Right? So every Kb is going to be 1 times 10 negative 14 divided by the corresponding Ka. You just got to look up the right Ka. Okay. So let's say we have this system. So we have OCl minus. Okay. So we have OCl minus. Or pick any conjugate base, F minus, whatever. The question is, how do you get the darn thing in the water? I want to put OCl minus in here. How do you do it? The answer was right here. How did we put Cl minus in water? We didn't put HCl in water. We said we put NaCl in water. So what's the word for that ion? Spectator ion? That's a technical word for it. It's always those group 1s, because remember their purpose? These group 1 metals? All they do is just get stuff in solution. They dissolve 100%, then they just sit there. I don't know if you remember doing those net ionic reactions. Whenever we crossed anything out, it was almost always lithium ion, sodium ion, or potassium ion every single time. I don't know if you noticed that, but we did. That's their only sole purpose is to make a solid. So you can pull it off the shelf and you can put it in solution. So you're not going to see a bottle with hypochlorite, OCl minus on it, but you will see a bottle with potassium hypochlorite. Right? It's going to be a solid. Okay. So what we don't want to get confused on in the homework, I think, is let's say this is the base that's in solution. They could say 0.2 molar potassium hypochlorite, right? And they say, hey, what's the pH of this solution? What's the initial concentration of OCl minus? If this is in the homework, this is the problem. What's the initial concentration? It's 0.2. Because remember, the K is just there. The K is just there to make it a solid so you can get it into solution. So that's the same thing. Well, you don't care about the potassium, but it's 0.2 molar OCl minus. And that's what you care about. And that's what goes in the I row, right? That would go right here if you were talking about OCl minus. Okay, you follow? Not so bad. I don't think it's too bad. Okay. But I really think the most confusing part is setting this stuff up. So these are just sample pretend quiz test questions. Okay? So you have access in your notes here, you have access to tables 16.1 and 16.2. So feel free to use these, table 16.1 and 16.2. Feel free to use them to answer these questions. Okay. Determine whether each solution will be acidic, basic, or neutral, and then write the reaction that controls the pH. In other words, you have to, if you say it's acidic, you better write Ka reaction. If you say it's basic, you better write Kb reaction. If you say it's neutral, you don't have to write any reaction. Okay? So all we're doing is setting ourselves up to do ice for the next part. Audrey, how would we do the first one? And then we'll let you have at it. Just make sure everyone understands this. Would you say that first one, 0.01 molar sodium cyanide, will be acidic, basic, or neutral when put in water, if it's aqueous? Which would it be? Now there's a hint. Audrey, there's a hint. Let me give you the hint. The hint is, you recognize what's out front? That alkali metal. So if that alkali metal is out front, that means they're probably trying to get a conjugate base into solution, right? Because alkali metal will never do anything. So what you're really looking for is that CN, right? So you can cover your bases and see if it's in this base ionization table, but notice there's never any alkali metals out front. In any of these, there's never any alkali metals. So that purpose of that alkali metal, I'm talking about this guy, the purpose of him is so that you can get one of these conjugate bases in, right? So that's a real strong hint. Just be careful that that conjugate base isn't one of the 6. So this solution will probably be acidic, basic, or neutral. Basic, because Cn minus is a conjugate base of HCN. And is HCN a strong acid? No. So it's not one of those trick questions then. So this will be basic, so you should say basic. And then it wants you to write the Kb reaction. So this, you could write sodium cyanide, but I think it's confusing. Just leave it out. Cyanide plus water. Hydrogen cyanide plus hydroxide. And then you're all ready to do ice, because they'll tell you the concentration. Oh, they did tell you the concentration of sodium cyanide. So 0.01 would go in the I row under the cyanide. We'll do that next. So anyway, look at each one of these, A through F, and write down whether it should be acidic, basic, or neutral. And then if you write acidic or basic, write the corresponding hydrolysis reaction. So it has to be a Ka or a Kb. And if you're lost, just ask so I can help you out. All you have access to are tables 16.1 and 16.2 to help you out. So Kendall, you see what's going on?
Okay, I'm just confused. So I find them on the table, so like this one.
Yeah, yeah, if you find it in the table, then you know it has to be a base.
Okay.
So you have to write the Kb.
And so it's same thing for this.
Yeah, so those are the easy ones because they are right in the tables.
Okay.
Yeah, those are easy ones. But the other ones aren't so.
What did you do for C? Basically.
And then you have to write the corresponding reaction too, though.
Oh.
Write the corresponding reaction too. But yeah, you got it, exactly. I agree with all those.
Okay.
Oh, but this one won't be neutral.
It's supposed to be basic, yeah.
Yeah, yep.
Ask him.
Write your K, oh, you did, good job. Was this making sense?
I got base for that.
Yeah, because it's in the table.
Yeah.
And that's the ones in the table. So you'd write the corresponding Kb and the Ka. Now these guys, like he's not in the table. But there's a good hint. You see that alkali metal. So you should really be looking for HOCl and see if HOCl is in the table down here. Well, HClO, same thing. So that means that ClO's got to be a conjugate base. So pretty much whenever you see that bloody alkali metal, it's going to be basic. Just be careful. Like here, same idea, it's going to be basic, but Cl minus is the conjugate base of one of those 6 strong acids. So it's not going to form hydroxide, it's too weak. So this would stay neutral. Okay, do you agree with my answers for B, C, and D? B basic, C basic, D acidic? You agree with those? Okay. Then we need to write our, if it's basic, we need to write our hydrolysis reactions. All right? Agree with all of those? Mia, you agree with all those? Excellent. Megan? Okay, jump to F. How'd you answer F?
I said it was basic. It's the HClO4 is
Yes, except that you fell for the trick. It's one of those 6 trick questions, right? It's neutral, because you got to memorize those darn 6 strong acids. Do you remember HClO4, what was its name? Perchloric acid. You don't even hardly ever see that. We don't even use it in lab. But this is going to stay neutral. How about E? Same thing, because you recognize HCl. Okay, so if you can do what's here, there's nothing new. It's the same thing as last class period. It's the same as the quiz. If you can do what's here. Okay, so here, write the hydrolysis reaction and determine a value for its determine a number for its equilibrium constant. So it wants you to write the hydrolysis reaction, write the Ka or Kb reaction, and give a number for the Ka or Kb. So we've got sodium fluoride, potassium nitrite. All right. I'll give you a hint. Neither of these are neutral. So what all you do is you don't even mess with the sodium. Just write the Kb reaction for F minus. So it'd be F. It's always a conjugate base, F minus, plus water gives the conjugate acid plus hydroxide. And then you have to figure out what the KB is going to be. See what we get for this here. So I got about 1.47 times 10 to the negative 11 for my KB.
Okay, so you did do the H. Okay, so then you did.
So did you get about 1.47 times 10 negative 11 for your KB? Kemma, did you get that?
I was kind of lost. I couldn't remember. Like I got the here.
Okay.
I got that, and I couldn't remember. I didn't know this was the right thing.
Yeah, that wants a number for the equilibrium constant.
Okay. I see where we got. Like I see where we got the numbers, but I didn't see that.
So did you get the KB? Made sense? Okay. Oh, you're ahead. Very good. 2.2 times 10 negative 11. All right. If you got it, go on to B, and if you got B, go on to the next one, because you know all this is good practice. Hopefully you're writing another KB reaction. And here it is. So I got 2.22 times 10 to the negative 11 for KB for the last one. Excellent. So KW is what number?
14.
1 times 10 to the negative 14.
Okay. That's what's
KW is 1 times 10 to the negative 14. Yeah. Okay, I keep going. So remember, KW is 1 times 10 to the negative 14. Okay. So one more EX3 and then a full-blown problem on EX4. Oh, this guy, he's going to be in the base table. Where is it?
Yeah, right there.
Yeah, there's nothing to calculate. There's your KB. So the ammonia is in the weak base table. Sometimes they write it as ammonium. It's more common to write it that way. And from the table, you just get the KB. Whatever it is. I think it's 10 to the negative 5 or something. What is it?
Oh, I didn't get it for it's just I read the reaction.
Oh.
I didn't put any numbers.
Yeah, so I'll look it up. So I can write it in there. Oh, where is it?
Oh wait, no, the basis.
Yeah, the base table.
1.8 times 10.
Oh, I was going to guess that. 1.8 times 10 to the negative 5. Oh, you're right, Megan. They want the KB expression, not the KB number. Ouch. Okay. So see if you can, these make sense to you. See if you can answer these. There's only 2 left. And spring break officially starts. Put that work and effort in now, Kendall. It'll be a lot easier when you go home.
No.
Sir, we do this AB reaction.
Yep.
And we get KB from doing this.
Yep, exactly.
Plug it back in to the,
And then, so then this is going to be products over reactants of this.
okay.
But you need to make a little ice table, right? Because,
I was gonna say, because I already know how to do it.
but the ice table always, your ice table, you can almost jump to it. It's always x squared divided by the initial concentration. Always.
I just wanted to make sure it's right, because I already got it.
Yep. And you can, yeah, because you can drop that x, because that guy's negative 11. So it's pretty much always goes to that.
Thanks.
It's kind of got to be careful, because when you start making these quick jumps, this is where I screw up. I get the x, then I take the log of it, and I think that's my answer. But no, that's where the ice table helps you, because x is actually hydroxide and not H. So when you make these quick jumps, very often I end up screwing up.
Oh, it's in 4.
Yeah, I got it. She did it, just subtracted it. Right?
Is that how you fill out your table?
Yeah.
Good. They got x squared over 0.58. You just got to solve for the x now.
Yeah, I'm trying to do it now.
Yeah. So pretty much.
So do we do that?
What I think you should do is just get used to seeing how you do this in your head, then do it all in the calculator. So what I mean is you're gonna have to put this in the calculator first. Then you gotta take it times this, because that goes to the top. Hit equals, then take the square root.
Yeah.
So just be one step, then x equals.
Oh, okay.
Otherwise it gets confusing. See how you have equals on this side and equals on that side?
Yeah.
It gets confusing. So I would just solve it all in one step on the calculator. What was it? We saw it already. 1.47 times 10 negative 11. I guess we'd say POH. Did you get an answer? 8.47.
Oh, yeah, okay, I was like, why did you do this?
Okay. Oh, and here's a good hint. When you go through a lot of this work, right, we should get an answer for this one with a pH above or below 7. Above. If your answer isn't above pH 7, you know you did something wrong, because it has to be basic, because you dumped a base in water. So I'm going to scribble yours down. You got pOH of 5.53. What'd you get for your X, Bowdy? Yeah. 2.9 times 10 negative 6. And your final answer was? Okay. Bowdy got about 8.47 for this one. Okay, so did Steph. Good. Kendall did.
The second one's really close to the same.
Really? Okay. You guys got the next one done already?
Yeah.
What's the answer so the people at home who are skipping class can get it? You got what? 8.67. Excellent. So have a good break. Be safe.